So finally today, even though we've been studying advanced geomechanics for a month now, today's the first day we actually cover something that's specific to geomechanics and not necessarily just generic continuum mechanics. So just a reminder, we can decompose our stress tensor into a deviatoric part plus an isotropic part. And we often write that isotropic part as the pressure, where the pressure is defined like this. And in this case, the minus sign comes about because we typically talk about pressure in terms of being positive in compression. But in this case, we're defining our stress tensor as being positive in tension because it's a little more convenient to do it that way. So when we model a poroelastic solid, we model it as a continuum or a mixture. So in other words, we make the assumption that the pores are very small compared to any representative volume element that we would. This is the size of an element in a computation or the size of a sample in an experiment. That the representative overall properties of the mixture of the pores in the solid, okay? That the pores are essentially equally distributed and very small compared to the solid, okay? So that's a sort of overarching assumption of poroelasticity. And so what we want to start by doing is let's look at a solid material that's under hydrostatic compression. So what I mean hydrostatic compression, that there's an equal stress on all sides and the sample is in equilibrium. And since it's equal on all sides, we'll just define it as P. So there's some pressure, okay? Except our solid is not a solid completely. It's a porous material, so it's going to have pores inside of it. And obviously, I'm drawing these pores much larger than what they really are. The pores would be equally distributed and microscopic compared to the size of the sample I've drawn. And each of these pores, we're going to assume that they're fully saturated with a fluid. And since the sample is in equilibrium, they're applying an equal and opposite pore pressure to the solid skeleton. So there's an equal and opposite pore pressure such that the solid skeleton is in equilibrium. And so if we look at a little equilibrated patch of the solid skeleton, like this, again, it's equilibrated with the external pressure and the pore pressure, right? So the stress in that little equilibrated patch is going to be sigma ij minus P delta ij. According to this decomposition up here in the top, and because it's completely hydrostatic, there's no deviatoric stresses. So there's only pressure. Okay? And so if we now look at a constitutive law, remember before we had that we could write the constitutive law for an isotropic solid as 2 mu times the deviatoric strain plus the bulk modulus. And I'm going to be really specific here and say, because we're talking about this little equilibrated patch of solid material here. So we're talking about the bulk modulus of the solid material, okay, times sigma kk, I'm sorry, epsilon kk delta ij, right? Well, again, this is a hydrostatic compression, so there's no deviatoric strains. And then, so you're just left with this equation that we can solve for the volumetric strain, sigma kk. Right? So if we just multiply both sides by the Kronecker delta function, then that would, let's just do it to be explicit. So you'd have sigma ij, which is 3 and 3, which you could then cancel from both sides. Right? And then we could solve for the volumetric strain, sigma kk, which is minus the pressure over the bulk modulus of the solid. Okay? And then if we plug that back into the total strain, right? So the total strain, just using our same type of decomposition, so the total strain tensor is the deviatoric strain plus 1/3 epsilon kk delta ij. There's no deviatoric strain, so the total strain is, plugging this in here, the total strain is minus P over 3K times the solid, K of the solid, delta ij. So this is the total strain in our little solid patch. Okay? So I guess put this in a box, hold on to it. Now, if you go back to generalized Hooke's law, in additional notation we had this. I may have never explicitly mentioned it, but this is an invertible relationship. So we can solve this equation for epsilon KL, and the solution would be this guy, where D is the inverse of C, or C I J K L D M N O P is equal to I M J N K O L P. This is a fourth order identity tensor. So we'll use that relationship in just a second. So now if we apply an arbitrary stress and pressure to our poroelastic body. So the arbitrary stress could come about because of mechanical deformation, okay, which then could, the pore pressure could come about due to fluid flow, change in fluid flow, okay. A change in the pressure could come about because of that. So then the strain, using this inverted relationship, the strain of our entire skeleton, right, the entire skeleton is, according to Hooke's law, any stress that comes about due to mechanical deformation plus any pore pressure change, okay, minus those equilibrated volumetric strains in the solid skeleton. So here I'm just writing down all the total strain is equal to Hooke's law of the skeleton minus those equilibrated volumetric strains that we put in the box earlier. And this would be, again, the inverse of C, where C would be the constitutive tensor of the solid skeleton. So if you went into the lab with your poroelastic material and you drained out all the fluid and then you did a bunch of tests, this is where you would populate C, right? So that would be in the so-called undrained limit. Okay, so we would, I'm sorry, the drain limit. It would be in the drain limit, the pore pressure equal to 0. Okay, so now I'm going to introduce something called an effective stress. And we're going to use the symbol sigma prime. So we're going to say that sigma prime is the stress in the solid plus an undetermined coefficient alpha plus the pore pressure times the identity matrix. And that is going to be equal to C ij KL epsilon KL. All right. So now let's plug in what we have for epsilon KL up here. So that's going to be equal to C ij KL d KL ij sigma ij plus P ij minus 1 over 3 KS P KL. All right, and remember we said that this is that fourth order identity tensor. It's equal to IK JL JL KI J, right? And that whole thing multiplies sigma ij. And if you went through all the contractions here, remember anytime you have an identity Kronecker delta function times a tensor, you pass over the repeated indices, right? So if we just did it one at a time, if sigma ij would become sigma il, and then it would become sigma KL, and then it would become sigma kj, and then it would become sigma ij, right? So all of this just reduces to sigma ij when you do all those contractions. Okay? And so, let's look at the other terms. So we have, you're just bringing this one down, sigma ij plus alpha p Kronecker delta. That's equal to sigma ij plus p ij minus Cij KL over to 3 KS P KL. All right. What? What? What about it? Just the solid. Yeah. Yeah. They would both be of this. Yeah. Because that. All right. So then these cancel, right? I can subtract that from both sides. And then I'm going to multiply both sides of the equation by sigma ij. I'm sorry, delta ij. So delta ij, delta ij, delta ij. So that's 3. That's 3. So then if I divide both sides of the equation by 3, and also the p's cancel. You see there's a p in every term. So they all cancel. And ultimately I get alpha is equal to, so here I have 3 over 3, that's 1, plus delta ij, c ij kl, kl over 9 ks. So this thing, alpha, it's called Biot's coefficient. So you probably, if you had like an undergraduate reservoir geomechanics class or something, you probably saw, you might have seen Biot's coefficient, but you may not have seen it derived like that, where it came from. We're going to make it a little bit, we're going to make it even simpler. So for an isotropic material, this term would be 9 times Lemay's parameter plus 6 times the shear modulus all over 9. And if you were to look that up on Wikipedia, what you'd see is that that's equal to the bulk modulus. Now this is the bulk modulus, the total bulk modulus. So the bulk modulus of the skeleton structure, right? And so when we plug that back into the equation for Biot's coefficient, then you get 1 minus kt over ks. So again, kt is the bulk modulus of the total structure, and Ks is the bulk modulus of the solid, okay? So when Ks is much, much larger than Kt, alpha tends towards 1. And this would be the case of like unconsolidated sands, right? So in an unconsolidated sand, the solid structure is like quartz, right? And so the bulk modulus of quartz is much, much higher than the bulk modulus of, if you were to take a set of unconsolidated sand and go to the lab, right? Because you're going to squeeze, if you go to the lab and you test that, you're going to squeeze down all the pore space, right? And squeeze it down, and the bulk modulus of that structure is going to be much, much smaller than the bulk modulus of quartz, right? So in that case, your Biot coefficient would be approximately equal to 1. For rocks like shales or concrete, alpha could be on the order of like 2/3. So somewhere maybe between 0.5 and 0.8, just depending. And so just remember, this came about from this idea of effective stress, which we're going to use. So this is the effective stress equation. And you can see that if alpha equals 1, then it's also the effective stress equation. It's just the alpha doesn't show up, and that's probably the form you're more familiar with from undergraduate reservoir geomechanics. That's so-called Tergazi effective stress, versus the more general one would be the Biot effective stress. So Tergazi's definition is just a special case of the Biot, and more recently, people have generalized this idea to include a tensorial alpha. So that the most general form, and this is pretty recent work, would be such that this alpha would be actually a tensor. And that's not so much critical in rocks or things that are, for the most part, fairly isotropic. Not that rocks are that isotropic, but there can be other materials that undergo very large deformations, like aerogels and other things that can undergo very large anisotropic deformations, and in that case, you may need to go to like a tensorial formula for alpha. But this is what we'll use as a definition for effective stress in this class.